Dear students, this is the second lecture with the storage architectures. In the previous lecture, we have looked at the working of a simple flash memory cell, how to read, write, and erase the cell, and two possible arrangements of such cells in NOR and NAND type architectures. And we have left the discussion with the point that NAND architecture is used for all the generic purpose storage requirement. NOR architecture is used for embedded and IoT deployments. Now let's dive further into the NAND flash architecture. Here is a simple 2D arrangement of the NAND cells, NAND flash cells. A string is one column of such 2D arrangement, and the typical sizes of string is somewhere between 32 to 64 cells. It means that a string will have 4, 4 to 8 bytes of data, and string is the minimum read granularity when we are trying to access a NAND flash. An array is just a collection of strings. Now we have a notion of page, which is a row of such flash cells which share the single word line. Here it is shown, the word line is shown as the yellow line, and all the cells in a row will have the same word line. So they form a page. Typical page sizes are 32K cells to 128K cells. It means that the page size is somewhere between 4 kilobytes to 16 kilobytes. Now we have already seen the notion of page, the term page rather. When we were discussing the virtual memory, we had virtual pages, physical pages. Then when we were looking at the actual DRAM, we had the DRAM page. Similarly, here is flash page, and all of these can be any different numbers. Okay, there is no stringent requirement that the virtual page size, physical page size, DRAM page size, and the flash page size all need to be same. The page size also determines the minimum write granularity to the NAND flash. It means that even though I can read 4 bytes to 8 bytes from this flash uh, arrangement, but I can write only 4 kilobyte or 8 kilobyte of data at a time. I cannot write simple one word or one cache block amount of data. So there is a disparity with the read and write. This was not the case when we were looking at the SRAM and DRAM, even the registers. Continuing further, we have a NAND block, which is the 2D arrangement of such pages and strings. Now we can imagine a NAND block to be comprising of multiple NAND arrays. For example, if we consider a NAND block of 8 MB size, then it can have 512 pages of 2K cells in each, with a string or column of 64 cells. Together they make up our 8 MB. NAND block determines the minimum erase granularity. So we can read a string of data, we can write a page of data, but we need to erase a block of data. So This is mainly because of the underlying arrangement of NAND cells. There is a constraint with the fabrication. So at the architecture level, we need to consider these disparities to get the NAND cells working. Continuing further, such NAND blocks together form a plane, and a NAND die is collection of such NAND planes. So each NAND plane will have, for example, here n number of blocks, block 0 to block n minus 1, and each block has a collection of pages and strings. A NAND chip is collection of such NAND dies. It can be a single die or multiple dies, or it can also be a case that all these multiple dies are stacked in the third dimension to form a single NAND chip. Just a pictorial representation of the NAND. All these NAND dies are packed together, and here is a more realistic picture of a NAND chip with all its pins drawn out. So in the suggested material that I'm going to share with you today, skip the section 6, in which they have specifically discussed about how these NAND dies are formed into a single chip. That's not the main focus of from the architecture perspective. We just assume that there are multiple such chips available to us. Going further, we have a set of such chips. They are arranged into channels and banks. These chips are viewed by the SSD controller or the NAND controller as a set of channels and banks. A channel is typically the number of NAND chips that the controller can access in parallel. This is similar to what we have in the DRAM also. If the DRAM has multiple channels, all those channels can be accessed in parallel. The same with SSD. It means that each of these channels has a dedicated data bus and control address bus. In the figure shown here, there are 8 channels and the bus are shown in blue. We have separate buses. As you can guess, if we have more number of channels, we can do more data transfer in parallel, so better the performance it can be. Typically, low-end SSDs would have 2 to 4 channels. On the higher end, we can have as many as 10 channels. Now, the number of channels that a particular SSD can have depends on the performance that is required in the final system, the power that we can spend, and overall size of the SSD itself. The NAND chips, which are now can be viewed as multiple channels, can be grouped as banks. In the picture here, we have 2 banks, bank 1 and bank 2, and the memory controller has, the SSD controller has separate bank control signals. So one of these can be accessed or activated across any channel at a time. The NAND chips across different banks that form a channel share the bus. So for example, here this NAND chip and this NAND chip will share the data address and control buses of channel 0. Again, this is something similar what we have observed with the DRAM organization too. All the banks in a rank share the bus, and all the ranks of one particular DIMM share the bus. With all this in mind, now let's look at the SSD controller architecture. What we have is a set of NAND chips organized as channels banks. Internally, they are organized as dies, planes, blocks, pages, and strings. Here we have the host system, which is our pipeline followed by multiple levels of cache and followed by the DRAM. And whenever there is a page fault at the DRAM, the host system contacts the secondary memory, specifically the SSD controller, via an interface. This is an external interface. Many popular interfaces are there which are pretty much standard now. Serial ATA, in short SATA, we have a parallel version of it. Then we have the most popular USB. Then PCIe, peripheral connect interface, express version, PCIe. All these are pretty much standard data transfer protocols that the SSD needs to adhere to. Now the controller on one end will manage the NAND chips. At the other end, it will communicate with the host system to get the instructions on which particular data needs to be fetched, and accordingly it will issue the signals to these individual NAND chips, get the data and transfer it to the host. The same way, if the host wants to write some data to the NAND chips, the controller takes both the address and the data, finds the appropriate location and writes to it. So without the controller, the collection of these NAND chips is pretty much a dormant storage which cannot be used. So when we call a solid state drive, it is the collection of the controller along with the group of NAND chips with complete connections within themselves. Here is a more realistic picture of the SSD device on a PCB. Each of these rectangular chips are the NAND chips. There is another square chip here. It need not be particularly square, but here it is. This is our SSD controller, and here we have the SSD interface to which we connect the bus, which eventually gets connected to the south bridge of the processor, through which the data transfer will eventually happen. So we have covered sections 1 through 8 of the SSD 101 ebook that I'm going to share now. Skip section 6, which is on packaging. Further, in the next few lectures, we are going to dive into the SSD controller itself and look at various tasks that it needs to perform. I'll pause this lecture now. Thank you.